Okay, so this is chapter 9, section 5, more or less. We're going to do 1D and 2D, so we're going to do a little bit of 2 and 5 or whatever it is. But, okay, so this is, first we're going to talk about 1D collisions, just to get that kind of, 100% under our belt. So let's just do something in the X direction. Let's say we've got particle 1, this guy right here. Whoa. This guy right here, particle 1. We're going to send that into hit particle 2. Now, particle 2 has 0 meters per second. It's just sitting there, okay? And particle 1's going to hit it. The question is, what's the final of particle, what's the final velocity of particle 1 if it hits particle 2 and particle 2 has this final velocity? Now, there's a couple of ways to do this. One way is if the two masses are roughly equal, like in billiard balls, that could happen. We're going to look at that, but then we're also going to look at a little bit below what happens if those two masses are not equal. Okay, so what do we know? We have to conserve momentum, okay? That has to happen. So what are we going to do? We're going to say that in the I direction, the initial momentum is equal to the final momentum. Now, we know a lot of the things that we need to know about this. And when we write down those conservation of momentum equations, the first one we get is this one. And I've scratched through V20 initial, V2 initial, because V2 initial is 0. So that's going to 0, so we don't really care about that. So the only thing that we're left with is M1 V10, V1 initial. And that happens to equal this guy here and this one. But we really want this one, okay? That's the one we really want, so we're going to solve for that. So what do we say? We say M1 V10 minus M2 V2 final is going to give us our initial, our final M1 V1, okay? Great. So this is the equation that we're left with because we really just want to know what is this velocity. So that's our equation. Now, we can do a couple of things. If this and this and this are all the same, we can factor out the M1, M2s on top, and it cancels out with the M1 on the bottom. Easy, all right? And in that case, then we just say that V1 final is equal to V1 initial minus V2 final, and we show easily that V1 final is equal to 0. And that kind of makes sense, and you've seen it when you've played pool, I'm sure. For those of you who've played pool, you've seen the ball hits the other ball goes off with the same velocity that your ball had going in, and it leaves the other ball still, okay? And it just stops dead in its tracks. Okay, well, that happens. If we have different masses, so let's deal with two different masses. Well, now all of a sudden, we can go back to this equation here. We can put in M1. That's our M1. We've got our velocity here. We've got our final velocity here and our M2. Excuse me. Jeez, sorry. We're dividing by M1. And when we do that, we're going to end up with 1.8 meters. Okay, I'm sneezing, I'm yawning. Get over it. I'm good. Thank you, sorry. 1.8 meters per second is equal to our V1 final. And essentially, we did it two different ways, but we used the same conservation equations to develop an equation in the box here, this equation in the box that answers our question. Okay? All right. So this isn't exactly the same kind of example, but I wanted to do an example of an inelastic collision. Okay, so we're dealing with an inelastic collision. We've got a hockey goalie and they're stopping a puck. All right, now I'm not going to draw a hockey goalie very well, so I draw the hockey goalie as an amorphous blob. And now you can, every time you watch a hockey game, you can think of the goalie as an amorphous blob, and good luck. All right. So the goalie's sitting in front of the goal, and we were going to stop that puck. The mass of the puck, this is a regulation size puck right here. This is a regulation size goalie. I'm just kidding. I don't know. They don't want to be as heavy as me, but they don't want to be too light either. And a slap shot can get to be as high as 45 meters per second. So that's pretty fast, about 100 miles an hour. And that's going to come zipping in. We kind of don't know this. It's going to be roughly 0. Okay, but we don't know this. This is the initial. Yes, of course. Initially, the goalie is not moving. All right, maybe side to side or something, but no, the goalie's not moving forward or backward. It's just sitting there. Okay, they are just sitting there initially. So good. All right, so it's perfectly inelastic because the goalie and the puck become one and they move together as one body. All right, so here's what happens after the scene. The amorphous blob has absorbed the puck and they are one. Okay, so we want to know this question right here. What is VGF, or the velocity of the goalie final? And since they're one, that means that that's also the velocity of the puck finally. So it doesn't matter. You can use one or the other. I want to stick with the goalie because I care about people and not pucks. Everybody cares about the puck, I guess, if you're a fan of hockey. Okay, so initially, what is our initial momentum? Okay, so let's figure that out. So we've got the mass of the puck times its slap shot speed. We've got the mass of the goalie times the goalie's initial speed, which is 0. So that's going to be 0. So we keep this. We have added 0, and that means that we really only have this. Okay, fine. Now, what about our final velocity? Well, we've got our VGF, because I want to do the velocity of the goalie finally. And then it's the total mass. So it'll be the mass of the puck plus the mass of the goalie. Now, these two things have to be equal. Okay? Have to be. And that's how we're going to figure out what this VGF is. So it's easy. We can add these two things together. We know what these two things are. And we do a little algebra, and we end up with this equation right here. Simple. Plug in the numbers, and we get our final velocity of 9.58 times 10 to the minus 2 meters per second. It's very small. If you want to look at it without the scientific notation, it looks like that. And that works pretty well. Now, let's check our kinetic energies to see if kinetic energy is either less than, greater than, or equal to kinetic energy final. And we know that this collision is inelastic, so let's just make sure that we get what we want. So initially, we have this kinetic energy. Oh, sorry about that. We have this kinetic energy initially. That ends up being this, which, if we do the calculation, is 162 joules. All right? So that thing's flying through the air, going at our goalie, and the goalie absorbs it. What's the final energy? Well, that would be the mass of the goalie times, or plus the mass of the puck, times the velocity of the goalie finally, squared, divided by 2. Good. You do all that, and you end up with 0.345 joules. That is small, right? Comparatively, relatively small. So, in fact, we end up saying that the kinetic energy final is less than the kinetic energy initial. So our collision is inelastic, and that means we lost energy. We lost energy. How did we lose energy? The goalie absorbed it, and that goes into deformations. So let me write deformation. The goalie is deformed afterwards. They get bruises. They get scrapes. The pads deform. All kinds of stuff happens, right? And how much energy did the goalie absorb? Well, we just figure out the difference. So 162 going in, this much at the end. That means this much energy was lost, and that was most of the energy, and it was lost to deformation. Okay, so most of the energy was lost in this case to the deformation of most likely the goalie. How the puck didn't get deformed, that's for sure. So we have a deformed goalie at the end of that. All right, let's do 2D. So here we have a situation where we've got two particles. One particle here is coming in at a certain angle. It's going in, and eventually this particle is coming in at another angle with its mass and momentum, some velocity, and they're going to meet and hit here. And then afterwards, we've got this kind of thing looking afterwards. So I didn't do a great job here. I could have, let's separate these out into our two distinct particles. And one's going to go flying off to the left, and one's going to go flying off to the upper right. Okay. So we can break it down. We can break it down into, let's do this. We're going to break it down into our one initially, the momentum of one initially, the momentum of two initially, looks like that. The momentum of three, the momentum of one finally, and the momentum of two finally. Okay, and all of those angles are there. That's what they look like, and they're all with respect to the positive x-axis. So that's nice, and we can go from there. But what do we have to do? We have to break each one of those things down in terms of their x and y coordinates. So initially, we have the first particle in the x direction. We have the first particle in the y direction, the second particle in the x, and the second particle in the y. We then figure out their finals for the x's and the y's for both particles. And we can then apply the conservation of momentum, but we have to do it in two ways. You have to do it in two ways. You got to do all the x. Whoa. We got to do all of the x, and we've got to do all of the y. All right? So in the x direction, what we would say is P1 0 in the x, P2 0 in the x is equal to P1 final in the x plus P2 final in the x. There's another way to write that. That's this, and this is going to equal this and this. Okay? So that's one of them. Now this one right here, same kind of thing, but this is all in the y direction. That means this plus this is equal to this plus this. It's pretty simple. And then we solve those equations to get exactly what we don't know, or whatever the question is asking for, right? If we know all the stuff, we know a bunch of angles, and we know masses and velocities, final velocities, initial velocities, all those things. What is it that we need to know? Let's come on over here and talk about what we need to know. We need to know M1, right? So that's probably given. Here, let's write givens here. And we'll say M1 is given. M2 is given. Our V initial for 1 could be given. Our V initial for 2 could be given. So far, so good. But what don't we know? We don't know theta 1 initial. We don't know theta 2 initial. We don't know theta 1 final, and we don't know theta 2 final. So we have to have, we only have 2 equations. So we got to have a lot of knowns to come up with the unknowns. We also don't know our V1 final, and we don't know V2 final. So usually these are given. A lot of the times these are given. In our case, we probably should know most of these, and then we could solve for these two if we wanted. Maybe we pull one of these out and one of these out. That's often what happens, and then everything else has to be known, right? So we could try and solve for, say, this guy and this guy, and that's doable, okay? As long as we have the 2 equations, we can figure that out. So, okay, let's get back to what we're doing. So what is actually conserved? Well, it's the total. The total, I just did that. Stop. The total P initial and the P final. Okay, now, in our case above, we have a system of interest, and we're going to say it's 2 masses, but you got to have, 2 or more masses to do this. The collision is elastic, and we're saying it's perfectly elastic, so our initial and our final energies are equal. The center of mass of the system stays moving at a constant velocity. That's the whole point. The center of mass for the system is here. It doesn't matter where the particles are, and it's moving with some V center of mass. And before the collision and after the collision, that doesn't change. Okay, that's the whole point. So that is what's being considered conserved, right? That's what's staying equal. So you add all the masses together. In our case, we're doing 2 masses. If your center of mass is moving at a certain velocity, it's not going to change, right? Those 2 things are colliding. It doesn't matter. They don't care. Our initial momentum is equal to our final momentum. This is too simple, right? This is too simple for us. Really, that's so basic. However, do you ever know the velocity of the center of mass? That's our problem. We don't know what the velocity of the center of mass is. We got to break this problem down into the x and y coordinates and go back to the things that we're given. We're given the one particle's velocity, we're given the other particle's velocity, and we can solve everything using this notion, right? But we really don't know. We never figure out, well, we can, it's doable, but we never actually go through and say, oh, I want to know what exactly the velocity of the center of mass is. Go ahead, you guys should do it. Pick a problem and figure out what the velocity of the center of mass is. And you can do it. It's not that terrible. Okay, so we can also do this in 3D. All right. Am I going to ask you guys to do it in 3D? No. But you could. And it's just even harder. Okay. So don't worry about it. Nobody wants to. And we have computer programs. So like as a particle physicist, I was using computer programs that did all the energies and did all the momentums and all the directions. And it was even relativistic, so everything was handled, and I didn't have to think about it. All I had to do was program the computer to do it correctly. So I'm not going to make you do anything like that on a test. That's fine. So let's do an example. This is a pretty fun example. I like it. It's we've got a 20 kilogram body. It's moving in the positive x direction. It's moving at a speed of 200 meters per second when it explodes. So it goes into three parts. One part is a mass of m1 going at 100 meters per second. It's 10 kilograms. And it's going along the positive y axis. We're trying to keep it easy, right? We don't want a bunch of angles and stuff. The second part of the mass gets broken off, and that's part 2 is 4 kilograms, and it's going backwards. It gets shot backward in the minus I hat direction at 500 meters per second. So the whole question is, what is the velocity of the third fragment? All right, and that third fragment has to weigh, if you add up the other things, 4 plus 10 is 14, so that means if it was 20 in the original, we're not going to destroy mass, so that leaves us with 6 kilograms. So M3 is 6 kilograms. We want to know the magnitude and the direction of the velocity of this 6 kilogram mass. The question after that is how much energy was released in the explosion. Don't worry, we'll get to that. So let's do part A first. And let's just do a little coordinate action. You've got to draw out your coordinates. Okay, this is key. All right, we've got our coordinates. We're saying before we have this momentum. And I just calculated it out because sometimes in these problems, if you just calculate it out, it makes a lot of things more simple. You're not dealing with a bunch of variables. Now, this is what happened after. So this is our after situation. So I've got M1, V1, that's mass 1 going north or going up in the y-axis. I've got M2, V2 going backwards in the I hat direction, negative I hat. And then I've got some M3, V3. I don't know what the angle is. I'm just, because that one's going up and that one's going to the left, I'm trying to balance this out. I'm just trying to make it look balanced. I don't know if my drawing is very correct, but it doesn't matter. I have a feeling no matter what happens, because those two things are going in those directions, we need to have this component going down. Okay, so that's all I know. And we're initially starting with this in the positive I hat direction. What did I do here? Okay, so this has to be one component. But this is in the positive I hat direction. So in the end, we've got to have something going in the positive I hat direction. So I'm going to assume that our M3V3 has a positive component and it has a negative J hat component because of this guy up here. All right, well, there you have it. So what have I done? I went through and I figured out this guy is going in the J hat. I figured out this guy is going in the negative I hat. And if we start doing our conservation of momentum, our cons of mom, we've got our initial in the X is equal to our final in the X. Well, we calculated. This is our initial in the X. We know that this is going in the positive X direction. We know M2V2 was going in the negative X direction. So we're going to take this positive one and subtract this negative one from it. If you want to solve then for this, then that's fine. You can do it, and it equals that, right? Because 4 plus 2 is 6. Okay. Now, we don't know what, I guess we do know what this is, but we don't know what this is, and we don't know what this is. Okay, so this is the only one that's known to us, and that's two unknowns, and we only have one equation. We can't do it, so we got to have another equation. That's where the y hat direction comes in. But initially in the y hat direction, we only had p not y. That's 0, right? Nothing happening from the initial mass. It's not going anywhere in the y direction. So our p final is equal to our m1v1 that's going up. And then we've got this component of m3v3 going down, right? That's this. So we can rewrite that equation. That's not too difficult. And we rewrite that equation as m3v3 sine of theta 3 is equal to 1,000. Now we've got two equations. We've got this equation and we've got this equation. And we can then take those two equations and do a quick little thing that's so easy. Sine of theta 3 times m3v3, cosine of theta 3, m3v3. If we ratio those things, then these go away, and we're left with 1 over 6. And the sine over the cosine is the tangent. So we have this nice equation, and that gives us a theta 3 of 9.46 degrees. Really, really good. However, I want you to look at one thing. Theta 3 actually goes, there's the positive x-axis, so I hat right there. Theta 3 goes like this. So even though we calculated a positive theta 3, it isn't positive. We have to know that we're going down. Our computer spits out a positive, but we know that it's a negative, okay? So no matter what happens, we need to write in our answer, when we finally go and write our answer, this has to be a negative, right? So it's at minus 9.46 degrees, okay? Now, what are we going to do to get our velocity? Well, the simplest thing would be this equation number 1 here. And we just solve that equation number 1 to get our V3. And that's not hard. V3 is equal to 1,014 meters per second. Now, 1,014 meters per second, that's fine. The sign of the angle, I'm taking the positive because I don't care. I want the absolute value of this thing. I just want the magnitude. So I don't care if, whatever direction it's going, I don't care. So that gives me the absolute magnitude. So now V3 is 1014 meters per second at minus 9.46 with respect to the positive x-axis. Cool. Done. We solved it. Our next thing, though, was how much energy came from that explosion. So we know that KE final is more than KE initial. So what we're going to say is KE final, that there's no other energy in the system other than KE initial and the explosive energy. Okay, and that's really what we're after. We want to know how much energy came through the explosion. So we've got our energy for the explosion is equal to KE final minus KE initial. KE final is equal to KE1 plus KE2 plus KE3. And we figured out what all those things were. Well, we didn't figure out those yet, but we figured out their velocities. We know their masses. So if we know their masses and we know their velocities, we can get their energies. That's not hard because 1/2 m1 v squared, 1/2 m2 v2 squared, 1/2 m3 v3 squared. These two, this one and this one, they don't add a whole bunch, but this, our third particle, man, that thing is screaming. Okay, so it's got all the energy in this sitch. All right. So we add up all those things, and those things all add up to 3.63 megajoules. What is a megajoule? That's a million joules. So 3.63 times 10 to the 6 joules. And 3.63 times 10 to the 6 joules minus 0.4 times 10 to the 6 joules. I did it in this way because it's easy to see in megajoules. We can just drop the 4 into the 6 and we end up with 2. So we've got 3.23 megajoules is our explosive energy. And that's it. We're done. So we've seen a lot of good examples. We got a lot of good. Basically, we're dealing with vectors when we're dealing with momentum. So to sum it all up, you really, really need to break down your vectors into their components and add and subtract in the x and in the y directions and go from there. That's it. Okay. Congratulations, everyone. You've gone through another video.